Previously, we talked about what force a charge feels in a magnetic field. Now we're going to see what happens to the charge in the presence of an electric and magnetic field. Specifically, we're going to look at this problem here. So here we have an electron that is moving at a constant speed in the x direction, and then it enters a region where there is a constant electric field and a constant magnetic field. If B is in the y direction only, what electric field, magnitude and direction, will keep the electron moving in a straight line at constant speed? So we have basically two fields, electric and magnetic field, both exhibiting forces on the electron to keep it moving such that it has no acceleration. So here's the basic setup of the problem. First, let's choose a kind of coordinate system with x going to the right, y going up, and z going out of the screen. We have the electron. It's moving in the x direction, so its vector is given by v vector equals v times I hat, and then it enters the magnetic field region where the magnetic field is given by b vector times b times j hat. Now we want the electron to move straight across without accelerating, either increasing its magnitude or changing its direction. Both would represent acceleration. So we want to turn on an electric field and in a certain direction with a certain magnitude to be able to do this. So for the electron to have zero acceleration, Newton's second law says that the net force must be equal to zero. And the net force, as we said before, is made up of the electric force and the magnetic force, Fe plus Fb. And this must be equal to zero, which implies that the electric force must be opposite in direction but equal in magnitude. So the magnetic force, as we saw before, is given by Q times V cross B. Magnetic force is perpendicular to both V and B. So putting it in for our situation, we have minus E for Q and then V cross B, which becomes VB times I cross J hat. I hat cross J hat, of course, gives you K hat. Now let's note again that the V cross B term is in the K hat direction, but because it is an electron, which is minus E, the force will be in the minus K hat direction. So this magnetic force will be opposite to the electric force, and we can substitute it in and get an expression for the electric force of EVB times K hat. So in general, the electric force will be in the Z direction. The electric field, however, because it is an electron again, is an opposite charge, will be in the opposite direction, which is expressed through F equals Q times E. And putting in for Q, we have minus E times big E, and substituting from above, we get that. And then now we can solve for the electric field, in which case it'll be equal to minus VB times K hat, or in the minus Z direction. So again, the magnetic force is in the minus Z direction, the electric force is in the positive Z direction, but the electric field again, however, is in the minus Z direction. Okay, that's it. Bye.